AdamW and L2 are not the same, and that mistake changes how your model trains. I'll show the difference in PyTorch and how to use real weight decay correctly. By the end, you'll be able to build a workflow like this, which compares true weight decay to an L2 penalty and picks the option that lowers validation loss. I'm Professor Pi, teaching AI foundations with simple Python. Regularization is one of those topics that sounds small, but changes everything in practice. You tune a learning rate, add epochs, and then your model still overfits. Weight shrinkage often fixes that. People reach for weight decay to keep weight small and reduce overfitting. But many frameworks and optimizers blur two different ways of shrinking weights, and that confusion leads to suboptimal training. At an intuitive level, there are two ideas. One is adding an L2 penalty that nudges gradients by the parameter values. That changes the direction of updates during backprop. The other is decoupled weight decay, which simply scales parameters down after the gradient step. Both reduce weight magnitudes, but they behave differently with adaptive optimizers. For small models and toy data, you can see large effects. For modern networks, they interact with learning rates and momentum and alter generalization. In this video, we will build a tiny regression experiment in PyTorch. We will run a simple forward pass to measure baseline loss. Then, we will compare Adam with an L2 penalty to AdamW, which applies true weight decay. Next, we will train both for a handful of steps and measure validation loss. After that, we will show how to exclude bias from decay. Finally, we will sweep some decay strengths and pick the best one. Keep calm. The code is simple and the experiments are small, so you can reproduce everything. Now we will run a baseline forward pass. This snippet runs a forward pass and computes MSE loss using a tiny PyTorch linear model. We first set a manual seed so the weights and results are reproducible across runs. The tensors x and y hold a small, visually clear regression mapping from input to target. We create nn.linear to model a simple y equal wx plus b relationship, and define MSE loss to measure prediction error. The variable p stores predictions from m of x, and loss phi n compares them to y to produce a scalar loss. If you increase spread or noise in y, the loss will rise accordingly. The printed baseline loss shows our unregularized starting point before any optimizer choices matter. Next, we will compare a single optimization step for both approaches. This example compares Adam L2 regularization against AdamW true weight decay on one step. We reinitialize two identical NN linear models by resetting the PyTorch seed before each construction. The optimizer opt.L2 uses optim.Adam with weight decay, which adds an L2 penalty into the gradient. The optimizer opt.WD uses optim.AdamW, which decouples shrinkage from the gradient and applies direct parameter decay. After the single backward and step for each, we measure how much the weight norm decreased from W0. Larger weight decay will increase both effects, but AdamW's decay is cleanly separated. The printed norm drop values reveal distinct shrinkage behaviors for L2 versus decoupled decay. Now we will train both optimizers for a short run and check validation loss. This code trains two models with Adam and AdamW, then evaluates validation loss for comparison. We construct identical nn.linear instances by reseeding PyTorch before each, ensuring a fair start. The optimizers opt.L2, optim.Adam, and opt.WD, optim.AdamW, share the same learning rate and weight decay. We iterate 80 updates on the training pair XY, stepping each optimizer on its model. A small validation set, XV and YV, then checks generalization by computing MSE with loss FN. Increasing weight decay usually shrinks weights more, which can reduce overfitting but risk underfitting if pushed too far. The printed val losses make clear which optimizer generalizes better on held out points. Next, we will show how to stop biases from being decayed. This snippet excludes bias from decay using PyTorch.AdamW parameter groups. We build two identical NN.linear models. Opt.all applies weight decay to all parameters, while opt.prep assigns decay only to weight and sets zero decay for bias. After computing gradients with loss FN, we manually zero each bias grad, so any bias change comes solely from decay. Stepping both optimizers shows that opt.all still shrinks the bias via decoupled decay, but opt.grop leaves the bias almost unchanged. Increasing weight decay would magnify the movement in the all parameters case, while grouped decay remains near zero. The printed bias move values prove how grouping prevents unwanted bias decay. Finally, we will sweep a few decay values and pick the best on validation. This example tunes weight decay by scanning a few values and selecting the best. The list decays holds candidate strengths for AdamW's decoupled shrinkage. For each candidate, we reseed PyTorch and initialize an NN.linear to keep a fair identical start. We train for a short, fixed number of steps on X and Y using optim.AdamW. Then compute validation loss V on XV and YV with loss FN. The tuple best tracks the lowest loss and its decay value. Larger decay shrinks parameters more and can reduce overfitting, but too much will underfit. The printed best decay and best val loss show a small working baseline for practical tuning. This toy setup maps easily to a real project. Replace the linear model with a convolutional backbone. Expand the training set, and the same comparison still tells you which decay strategy generalizes better. The critical piece is preserving identical initialization and data splits so your comparison stays fair. Recap: AdamW applies weight decay directly to parameters after the update, while L2 via the optimizer mixes the penalty into the gradient. Use AdamW when you want clean, decoupled shrinkage with adaptive optimizers. One caveat: too much weight decay will underfit, so tune carefully. Next step, run a short grid search over decay values on a realistic validation split, and pick the decay that lowers validation loss. That single sweep often beats guessing a decay by hand. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.